Hello friends. So today we are going to discuss two questions, and both question was asked in the year 1994. So in the first question, two different coils having self-inductance L1 8 millihenry and L2 2 millihenry. The current in one coil is increased at a constant rate. The current is in the second coil is also increased at the same constant rate. At a certain instant of time, the power given to two coils is same. At that time, the current induced the current comma the induced voltage and the energy stored in the first coil is I1, V1 and W1 respectively. Corresponding values of the second coil at the same instant are I2, V2 and W2 respectively. Then we have to find out the ratio of I1, I2, W1, W2 and V1, V2. So this is a multi-correct option. Correct option rather. So in this case, we have in the question it is mentioned that the current in the coil is increased at a constant rate, and in the second coil it is also increased at the same constant rate, and we have two coils L1 and L2, and the current in first coil is I1 and in second coil is I2. So we start from that the constant current rate of increase. So we are given that current in both coils increases at the same constant rate. Increases at same constant rate. So we can write di1 of dt is equal to di2 dt, and let us suppose that constant k rate is represented as k. Okay, and at any particular instant it is also given that power supplied to both coils is equal. We are also given at a certain instant of time power supplied to both coils is equal. So from here we can say power in the first coil is equal to power in second coil. And the induced voltage is given as V1. So we can write, we know the general formula for induced voltage in inductor. We know that induced voltage in inductor, if represented as V, then V is equal to L di upon dt. So we can write this formula for both the coils. So we can say for coil L1, we can write that our V1 is equal to L1 di1 upon dt, and we assumed that di1 upon dt is equal to k, and L1 is given as 8 millihenry, so this will be 8 10 to the power minus 3 and multiply by k. Similarly, we can write for coil L2, that is our V2 is equal to L2 di2 upon dt, and it is given as 2 millihenry 2 raised to the power minus 3 and multiply by k. So from here we can find out ratio of V1 upon V2. So V1 upon V2 is equal to 8 into 10 to the power minus 3 multiplied by k divided by 2 into 10 to the power minus 3 multiplied by k. These two cancels out. This goes by 4. So we get from here that our V1 upon V2 is equal to 4. And it is also given that the power supplied at any instant is same, that is P1 is equal to P2. And we know that power to an inductor that is where P is equal to V multiplied by I. Therefore, we have two inductors L1 and L2. So we can write for L1, P1 is equal to V1 multiplied by I1. And similarly for our L2, we can write P2 is equal to V2 and this is I2. And we already know that P1 is equal to P2. P1 is equal to P2. We substitute the value. We get V1 I1 is equal to V2 I2. And we already know V1 or V2. So therefore we can write from here that the option it is I1 by I2. Okay. So we can write I1 upon I2 is equal to V2 upon V1, and V1 upon V2 is 4, so we get I1 upon I2 is equal to 1 upon 4. And finally, we come to the energy stored inductor. Energy stored in inductor, that is given as W is equal to half Li square. So likewise we have two inductors. So you can say for L1 we get W1 is equal to half L1 I1 square, and for L2 we get W2 half L1 I2 square. Now we can simply find out the ratio. W1 upon W2, we get this is half L1 I1 square half L2 I2 square. Half and half cancels out, so we get this as L1 upon L2, and here we have I1 upon I2 and its whole square. And L1 we already know is our 8 millihenry. This is 8 10 to the power minus 3, and this is 2 into 10 to the power minus 3. I1 by I2 we just found out is 1 upon 4, and this comes whole square. 3 goes away, this goes by 2. And we get W1 upon W2 is equal to 2, and this comes as 1 upon 16, and this comes as 1 upon 8. I think, let me check L1 and L2. 8 and 2 millihenry. Yeah, this is correct. Yeah, sorry, my mistake. This goes by 4, not by 2. This goes by 4, and so here it is also 4, and this now comes as 1 upon 4. So we get W1 upon W2 is equal to 1 upon 4. So we have W1 upon W2 is 1 upon 4. So option number C is correct. Option number A is correct. And option number D is correct. So A, C, D are the correct options for it. Option A, C, D are correct. So this completes the first question. Now we come to the second question. And in the second question, it is given that two parallel vertical metallic rails A and B, AB and CD are separated by 1 meter. They are connected at two ends by resistances R1 and R2 as shown in the figure. A horizontal metallic bar of mass 0.2 kg slides without friction vertically down the rails under the action of gravity. There is a uniform horizontal magnetic field of 0.6 Tesla perpendicular to the plane of the rails. It is observed that when the terminal velocity is attained, the power dissipated in R1 and R2 are 0.76 watt and 1.2 watt respectively. Find the terminal velocity of the bar L and the values of R1 and R2. So we are given figure. There are two rails AB and AC and connected with the help of resistance R1 and R2, and we have a sliding arm which is called as a bar L, which is sliding in downward direction by the action of gravity, and at some instant this attains a terminal velocity. And this entire is in the magnetic field which is horizontal and that is perpendicular to the plane of the rails. So it is perpendicular to the plane of the rails. So first of all, let us try to analyze the terminal velocity and the forces which are acting. Terminal velocity and forces. So first force will be the gravitational force that will be acting in downward direction. Gravitational force acting downward. Let us suppose that is given as Fg, and this Fg will be equal to mass into acceleration due to gravity. So this comes as 0.2 and 9.8, and this comes as 1.96 newtons. Another force, because this entire system is in magnetic field, so there will be force due to magnetic field, and that will be acting in upward direction. So we can say magnetic force which is acting upward. Let us call that as Fm. Now in this case, because it's said that the bar is moving at a terminal velocity, so the bar moves with a constant velocity, and that is going to induce an EMF, and that EMF is going to induce a current, and which produces a force which is opposite to the gravity. Okay, so magnetic force is acting upward direction, and that will be produced because of the current induced because of the bar which is moving in the downward direction in the presence of the magnetic field. So we can say at terminal velocity, the bar moves at constant velocity, let us suppose that is given as V, inducing an EMF that drives a current producing a force opposing gravity. So we can find out the induced EMF. So we can see our EMF is equal to B, magnetic field, length and velocity V, and which comes as magnetic field 0.6, length is given as 1, multiplied by velocity V, and this comes as 0.6 V. Now we have two resistors R1 and R2, and these two resistors are parallel across the bar. You can say R1 and R2 are in parallel across the bar. Therefore, the equivalent resistance R equivalent will be equal to R1 R2 divided by R1 plus R2, and the current, if the total current is I, then this current I will be equal to EMF divided by R equivalent. So you can say that total current I will be equal to E divided by R equivalent, and EMF we already know is our 0.6 V, and this comes as our R1 plus R2 divided by R1 divided by R2. Therefore, the magnetic force, one second, let us call this as FB, not FM, because this is force due to magnetic. So we can say the magnetic force that is our FB will be equal to IL multiplied by B, and we substitute the values, we get our FB is equal to, we already know the value of current is our 0.6 V R1 plus R2 divided by R1 R2, length is given as 1, magnetic field is about 0.6, and we get our magnetic field B, FB rather, FB will be equal to 0.36 V, and this comes R1 plus R2 divided by R1 by R2. And at terminal velocity, downward force will be equal to upward force, that is FB is equal to FG. At terminal velocity, we have our FB is equal to FG. We substitute the respective equations, we get this as 0.36 V R1 plus R2 divided by R1 R2 is equal to 1.96, and from here we can write that our velocity V will be equal to 1.96 R1 R2, and this is 0.36 R1 plus R2. Let us call this as equation number 1. Now it is also given that the power dissipation, so let us power dissipation so we have two resistances R1 and R2, and we can find out that the current R1 and R2 is parallel. Okay. So this is something like this. We have here our R1, and this is our bar L, and we have here R2, and we suppose that the current flowing through R1 is I1 and through I2 is through R2 is I2, and as they in parallel, so the induced EMF will be same, that is E. So we can write that R1 and R2 are in parallel, so voltage across each is the induced EMF, and from here we can write that our I1 will be equal to induced EMF R1. Induced EMF we already know is 0.6 times V divided by R1, and we can write our I2 is equal to induced EMF R2, which comes as 0.6 times V, and this is our R2. And we can find out that the power dissipation, that is our P1 rather. For R1 it is P1, so we can write that our P1 is equal to I1 square times R1, which comes as 0.6 V R1 whole square multiplied by R1, and this comes as our 0.36 V square upon R1. And the power dissipation is given to us. We are given power dissipation is 0.76. So this is equal to 0.76. Let us call this equation number 2. And similarly, we can write that our P2 is equal to I2 square R2, and this comes as, it will be same, that is 0.36 V square divided by R2, and it is given as 1.2. Let us call this equation number 3. And now we can use the relationship and try to solve and find the values. So first of all, let us divide P1 and P2. P1 divided by P2 is equal to 0.36 V square upon R1, and here we get 0.36 V square upon R2, and this comes equal to as 0.76 divided by 1.2, and here these terms will cancel out with each other, and this gives us that our R2 by R1 is equal to 0.76 divided by 1.2. And From here, let me solve it a little bit. We can write that our R2 is equal to 0.76 divided by 1.2 times R1, and which can be written as 76 divided by 120 times R1, and this comes as 90 by 30 times R1. Let us call this equation number 4. Now we are going to solve for solve for V, velocity rather. So we can say solving for V using P2. And we already know P2 is our 0.36 V square upon R2 is equal to 1.2. From here we can write our V square is equal to 1.2 times R2 divided by 0.36, and we just can modify it, and we get, or we can write that our V2 is equal to, this will be our 120 divided by 36 times R2, and that can be written as 10 times R2 divided by 3. Now if we substitute the value of R1, we already know the relationship between R1 and R2, which is equation number 4. So we can say using equation 4, we can write that our V square is equal to 10 by 3 times, and this is our 19 by 30 times R1, so which gives us that our V square is equal to 19 by 9 times R1. So let us, this was our 4, and let us call this as equation number 5. Next, we are almost done now. So we know the relationship between VR1 and VR2. Okay, let me write it here. So we know that our V square is equal to 19 by 9 times R1, and V square is equal to 10 by 3 times R2. And we already know the equation of the velocity, and that equation is our equation number 1. So we substitute this in equation number 1. So using equation 1, we get V is equal to, this comes as 1.96 times R1 multiplied by 19 by 30 times R1 divided by 0.36, and this is R1 plus 19 by 30 times R1, and this gives us that our this comes as R square, and we can write this will be equal to 1.96 multiplied by 19, and here we have multiplied by our R1 square divided by, this is our 0.36, and taking R1 is common, so this comes 30 plus 19, that is over 49. 49 times R1, and 30 and 30 are going to cancel with each other. Yeah. So here this R1 goes with this square, and if we square both the sides, we can write that our V square will be equal to 1.96 multiplied by 19 divided by 0.36 multiplied by 49 whole square, and this is our R1 square. Now V square and R1 we already know relationship, so we substitute here, we get this as 19 by 9. Yeah, so we write it, and that was a relationship, equation number 5. So we say using equation 5, we can write this as 19 by 9 R1 is equal to 1.96 times 19 divided by 0.36 multiplied by 49 whole square, and this is R1 square. R1 square, this cancel out with this. So therefore, we are going to get the value of R1, and that value of R1 will be approximately equal to 0.474 ohms. And we already know the relationship between R1 and R2. So we know that, but R2 is equal to 19 by 30 times R1. So this becomes 19 by 30, and here we have 0.474, and this gives us that our R2 is approximately equal to 0.3 ohms. And we already know the relationship between V and our R1. Therefore, we can say that our V square is equal to 19 by 9 multiplied by 0.474, and this comes approximately equal to 1. Therefore, V is approximately equal to 1 meter per second. So we found out the value of R1, R2 and the velocity, and that was the required. So these were the two questions asked in the year 1994. So let me summarize it here. So our velocity V, that is the terminal velocity, is 1 meter per second. Value of R1 is our 0.474, and value of R2 is our 0.3 ohms. So this completes these two questions. Thank you.